Hi, my name is Paul, and I'm going to talk to you today about cryptocurrencies and blockchain. Why do cryptocurrencies work? And how is the blockchain so magic? My name is Paul Oliver. I'm with Google. And of course, this video is not an official Google video, so do not take any of these opinions as anything but my own. My Twitter handle is at @itspaultastic. So my plan today is to first eat our crypto vegetables, as they say. We're going to cover things like hashes, signatures, and keys. And then we're going to talk about a simple cryptocurrency and then expand on that and talk about what problems they have. And then we'll go into the Bitcoin blockchain and see how it solves the problems that we run into. So how does Bitcoin secure transactions? This is the number one question that we're going to resolve today. Now, you probably have heard of the Byzantine Generals Problem if you've been paying attention to Bitcoin, and this term was coined by Lamport, Shostak, and Peace in 1982. But basically, the problem is this: let's say we have 4 generals surrounding a city, and they want to coordinate an attack. Let's say tomorrow at 2 p.m. So they send a message to each other, and therefore they say, hey, we're going to attack at 2. Are you in? Let's go. Let's do this. The problem is that we're sending this message across a hostile environment. There are people in the town that may see the messenger and rip the paper out of their hands and change the time or hand them something different. Or perhaps the messenger is wanting his general superior to fail so that he looks good and perhaps gets promoted. This was an altogether common problem in the Byzantine army, so that's why they call this the Byzantine Generals Problem. The paper, which was published in 1982, wasn't able to solve the problem, and this was a crucial problem at the time because they wanted to figure out how they can be 100% sure that the missile attack command coming from headquarters was accurate and was authentic, and that way they weren't going to cause World War III because of an invalid launch command. Now, they were not able to solve the problem. They ended up saying we're always going to need a central server with time-stamping ability to prove that messages are valid. But fast forward maybe 16 years, and you'll see Satoshi Nakamoto writes the Bitcoin white paper and releases this. Now, I highly recommend you read this. It's easy to get through, even if you're not super techie. But it covers a lot of the stuff we'll talk about today, and it's not that long of a document. Satoshi came up with a system where miners can verify transactions, and this is what you're going to see a lot with Bitcoin information. Yeah, miners are verifying that a transaction from Bob went to Anna properly, and there is a public ledger involved. You know, when we send Bitcoin to each other, it goes into the public, and the miners are verifying this. But how does that work? And before we get into the details of how it works, let's talk about some crypto basics. So we'll start with hash functions. And many of you in the audience are probably very familiar with hash functions, but it's important to go back and just look at their properties. So a hash function basically takes some input string and outputs a fixed size output. If you modify just one little bit of that message, perhaps put an extra space in there or capitalize a letter, it will drastically change the output. So this makes it easy to see if a string's been tampered with. It's also collision-free and allows you to hide information. So a property of hashing is that it is collision-free, as I mentioned. Now, what this means is that nobody can find 2 inputs that result in the same hash. So if I have some input string and it outputs the hash on the right, B82, and so on and so forth, and I said, find another string that has that exact same hash, and let's say it's this FASDL such and such. It's not, by the way, because I can't find the other string that would result in the same hash, but let's just say it is. This is impossible to do. So I said hashes are collision-free, and that's not entirely true. Obviously, hashes are a fixed length output, and so it would be impossible to say it's completely collision-free. So if you did try 2 to the 130th power randomly chosen inputs, which is basically the number 1 with 39 zeros after it and some change, there is a 99.8% chance the 2 of them will collide. But this takes too long to matter. If every computer ever made was computing since the beginning of the universe until now, the odds that they would have had found a collision where two inputs had the same output, this would be infinitesimally small, basically less than the odds of a meteor hitting the Earth in the next 2 seconds. We're still here, so collision free. Here's another application we could do with hashes. We could, since they are collision free, you could compare two big files, for example, by not comparing them byte by byte, but instead comparing their hashes. And this is what systems would use. Let's say you have a tool that finds duplicate files in your hard drive. This is what it's doing. Or to detect if a file has changed, we just check the hash. We do not check byte by byte if the file has any differing data on it or data in it. Because hashes are impossible to guess the input, you can also hide information in them. And so if I give you the hash and I say, guess what the input is, good luck. You're not going to be able to find it. This is what we could do with this. We could prove the commitment to something on an envelope, for example. If I handed you an envelope that was sealed and on the outside there was a hash, I could say, don't open this until February 2019. And then let's say you do, and you open it up, and here's the message that I wrote. I predict that the Nebraska Cornhuskers will win the national championship in 2018. Sign my name, put a date, and then you hash it, and you confirm that it matches what was on the envelope. So what this would provide is a way to prove that that was the information that was in the envelope the whole time. You just didn't know what the information was until you opened it. A hash function basically functions like this, and this is the Sha-256 hash. We first take the message and break it up into blocks, 512 bits. Odds are your last bit will not be last block will not be 512 bits exactly, so we pad it so that it matches the 512 bit length that we're expecting. And then there's an initialization vector that's 256 bits. And if you want the details of that, go read the spec for SHA-256. But we take those 256 bits and we combine it with the first block of the message. And it goes through a compressor function. And this compressor function takes all those bits and it outputs 256 bits. So we're putting in more bits than we get out, right? So we take the output of the compressor function and we now combine it with message block 2, an additional 512 bits, and that goes through the next compressor function, and so on and so forth till we get to the last block or the last compressor function, and the message block 3 that gets combined with the output from compressor function 2, and that gets output into the final hash. And that's the gist of how a hash would work. Now, SHA-256 is not the only hash function there is, but there are lots of different hashes, but this is a pretty standard one. It's a very good one to use. Now, since we know about hashes, let's talk about a hash pointer and how these can help us. A hash pointer is a pointer to where some information is stored, along with a hash of that information. So it allows you to ask for the information back and verify that it hasn't changed. Throughout this talk, I'm going to use this sort of diagram to show what a hash pointer would look like. You see an H with parentheses pointing backwards with that red arrow to the data. So when you query it and you say, hey, where's this data? And you get it, and then you hash it, you make sure it matches, you know that, hey, this data hasn't changed and it's where it should be. With a hash pointer, this gives us the ability to create our first simplistic blockchain. Here on the screen you see 3 blocks, and each one is pointing to the one prior to it. And then there's a final hash pointer, which is pointing to the most recent block on the blockchain. And the use case for this is a tamper-evident log. If you wanted to attack this blockchain, let's say we wanted to go back 3 blocks, so the third to last block, and let's change it. So the adversary attacks it and changes the data somewhere in the middle of the data, and that data is now changed. We're going to mark it with a red lightning bolt that it's changed. But now we have a problem because the hash pointer in the next block is now incorrect. The address might be right, but the hash is different. So we'll know right away that it's been tampered. So the adversary must go in and change the next hash of in the next block that's pointing back to the previous block. So now we have to change this, and the adversary now has another problem because the next block has a problem and needs to be modified, and so on and so forth. So now we change this next block, and the final hash pointer that points to the most recent block can't be changed and by the adversary. So she's in trouble and she can't tamper with this at all. So this is basically why a blockchain works so well for a tamper-evident log. Another data structure used in cryptocurrencies, which is very similar to what we just saw, is called a Merkle Tree. And this wasn't coined by Ralph Merkle, who invented it. And basically it works like this. Instead of hashing a large amount of data, let's say a gig of data, you can break it into smaller blocks. And each of those blocks can now be pointed to by smaller hash pointers. So let's start at the first block of data on the bottom left part of the screen. We have a hash pointer pointing to it in the parent node. And then on the right, we have a hash pointer pointing to the next block. And if you travel up the tree, you'll see that each of these nodes are pointing to a hash of the left block and the right block. Using hash pointers to the left and right block. So this is a cool feature for cutting down on the amount of processing power you need to confirm that a block is valid. So instead of like rehashing a gig of data and making sure that number hasn't changed, you just have to prove that a smaller block belongs in the Merkle tree. This is block number 4. If somebody hands us this block and says, has this been tampered with, all we need to do is travel up the tree and check the hashes moving up until we get to the root of the Merkle tree. That's at the top, and once we verify that it's correct hashes all the way down, we know that block does belong in the Merkle tree. This allows us to verify that the block belongs in the tree with big O of log n time complexity. This is a huge savings for nodes and for cryptocurrencies. This is what's used by Bitcoin. This is what's used by Ethereum and other cryptocurrencies that are quite popular. So as I mentioned, the advantages of this is that it can hold many items. You just need to remember the root hash. You don't have to remember all the hashes throughout the tree. And you can verify membership in big O of log n time. Now let's move into digital signatures, another key aspect of cryptocurrencies. So with digital signatures, we want a few properties. We want the ability to sign it, but only ourselves can sign it. But anyone can verify. So the signature is tied to a particular document, and we can't basically cut and paste it to the pen to another document and say, "Oh, I must have signed this other document too." No, that can't be done. You can only sign a document, and it can't be used to sign fictitious documents. As an aside, let me tell you a little story here. First, I must ask, whose bus is this? And it may not be obvious to you, but this is a Google bus. The telltale sign here is right in the front windshield. You'll see G bus to MTV, and that's the only indicator you'll see on the outside that this is a Google bus. On my first week of the job, I needed to travel to Google Building 45 from my hotel in Cupertino and go to some training classes that I needed to take. And I've done Google buses a few times, so I got into the hang of it. It's pretty easy. The bus stops aren't public, but you have an app that tells you where the bus will meet you at, what time. It's a really nice thing, and the buses inside are great. They have Wi-Fi, and they're incredible. They're so great that many companies in the Bay Area have actually copied Google, and they have very, very similar buses to do the same thing, take you around to your offices. Now, I had gone to the bus stop, and I was doing really good on time. And I came around the corner and I see the bus just pulling up and people are lining up. I checked my app again and it says the bus is coming in 5 minutes, but here it is. So I figured, hey, the app's wrong. I better hurry up or else I'm going to have to wait, a long time for the next bus. So I basically speed walked to the line and I got in line there and I got on the bus. And I held up my badge and I scanned it. And, they have a little badge reader to make sure you actually are authorized to ride the bus. And the badge reader turned green, and I sat down and took my seat. Didn't take too long, though. I noticed that we didn't turn where I expected it. It continued driving straight, and I started wondering what's going on. The driver must not know where he's supposed to be going. Then I looked around, and I noticed that there was a little Twitter logo on a window in the front. That was the only indication that this was not a Google bus. And so as I started Googling to figure out where the heck am I going, I quickly discovered I'm going to San Francisco. Not to my normal 15-minute bus ride, but I'm taking over an hour-long bus ride to San Francisco. And training starts in a half hour. So it was a big deal. I ended up getting to San Francisco, getting to Twitter headquarters. And I get off the bus, I kneel down, pretend I'm tying my shoe, because I'm very smooth. And as all the Twitter workers walked past me into the building, I turned around and went around the corner and got on another Google bus, thanks to my handy-dandy app that told me when it was coming and where it would pick me up at. So I took the bus back all the way down to Mountain View, and I was 2 hours late to class, but I was able to salvage the situation. But the problem was that the fact that this bus was not obvious that it wasn't a Google bus. Boy, it would have been handy if there was a signature at the bottom and I could verify, maybe hold up my phone and confirm this was a Google bus. Let's say it said, I'm Google and this is a G bus, not a Twitter bus, and I could confirm that the signature was actually signed by Google. And that would have been handy here in this situation. So this is why digital signatures are useful. So let's imagine some APIs that we could use in our cryptocurrency and that come from digital signatures. First off, we need the ability to generate keys. Let's say we input a key size and it outputs two things: the secret key, the signing key, SK, and then the PK, the public verification key. Secret key is meant to be kept secret, private to you, and the public key is meant to be shared far and wide for people. Then we have a method for signing a message. Let's call it sign. It takes two arguments, an SK, the secret signing key, remember, and then the message. And what it will output is a signature that can be appended along, with the message we're signing. Again, remember, this only goes along with the message that we're signing. And then if we want to verify the signature on a message, we'd call verify, and it would take three arguments: the public key, the message, and then the signature, and it would output true or false. Is this valid or not valid? Here are our requirements for digital signatures. First, valid signatures, when we verify them, they should return true. So if you call verify with a public key, message, and a valid signature, we'll get true back. You can't forge signatures. So if an adversary knows your public key and sees signatures on other messages, she can't produce a verifiable signature on another message that you didn't intend to sign. Some facts about digital signatures and what we use in cryptocurrencies. First off, Bitcoin uses ECDSA, which stands for Elliptic Curve Digital Signature Algorithm. It relies on some really hairy math, and it is a best practice, very good crypto. But if you don't have good randomness, basically your private key has been leaked. So don't roll your own crypto, and Bitcoin is using very, very good crypto. So that brings me to my next point, is that public keys can be used as identities. And let me tell you more. If you see a signature so that when you call verify with a public key, message, and signature, and in turn returns true, you can substitute this as saying PK says message. This seems simple, but this is a huge, huge deal, and this is what makes cryptocurrencies so cool. When PK says message, PK is now an identity, not just a public key, but it's an identity. With that in mind, how do you make a new identity? Well, you just generate more keys. You can create a new random key pair, meaning a secret key and a public key, where the public key is your public name that you can use, and the secret key lets you speak for that identity. You control this identity because only you know the secret key. Because of this, you now decentralize the identity management. Anyone can make a new identity at any time. You don't need a third party to grant you an identity. You don't need some server out there that says, thank you for signing up with our service. This is your new identity that you can use throughout the internet. You don't have to do that. You can make as many identities as you want. There's no central point of coordination. The identity actually looks random, so it can't be tied to you. These identities are called addresses in Bitcoin. So when you see a payment address, you're not paying it to Joe Smith. You're paying it to a public key that belongs to Joe Smith. Or does it belong to Joe Smith? You don't really know. So with this gives you some nice privacy features, but a few things here. Addresses are not directly connected to a real-world identity. However, your activity is all public. So your transactions actually can be linked over time. So we don't say Bitcoin is anonymous. We say it's pseudonymous. If you set up an account with an exchange, they have tied your identity or your real world identity to a wallet address, to a public key. And, as you trace transactions back through time, you get that. So let's say you wanted to prove that you knew Trump was going to be president 10 years ago. You say, hey, I know you think this is crazy, but guess what? I knew this was going to happen. How would you prove that you knew this 10 years ago? A hash published in the classified ads in a old issue of the New York Times. Or B, a text file with your Trump prediction dated April 14th, 2008, with your digital signature attached. Or C, a public key that clearly belongs to Donald Trump. Or D, a secret key that clearly belongs to Donald Trump. The answer here is A, sorta. All that it really proves is that you made a prediction 10 years ago for Trump. It's still possible, though, that you made millions of presidential predictions and you published them in several newspapers and you just produced the one that turned out to be correct. So then the prediction may be less impressive once that's said. The text file doesn't work because, well, timestamps on text files can be forged. Change your calendar date on your computer. That's an easy way to do it, but it can be done lots of ways. A public key that belongs to Donald Trump, that's not very impressive. Everyone should have access to public keys. That's not a big deal. A secret key that clearly belongs to Donald Trump, now that's a problem. We should notify Secret Service if you have that, and he needs better security guys, I guess. But that doesn't mean that you knew he'd be president. That just means we got some security problems in the presidential office. Which of the following is true in normal usage? A, you sign a document with your public key. B, the secret key is for encrypting. The public key is for decrypting. C, if I have your secret key, I can decrypt your messages. Or D, if I have your public key, I can decrypt your messages. The correct answer here is C. We didn't get much into encrypting and decrypting with public and private keys, but I just wanted to cover this a little bit. Yes, technically B is true. You can encrypt a message with a secret key and decrypt it with a public key because that's how they work, but that's not normally how you'd use them. Same thing with D. If you have a public key, you can decrypt your messages. If they were weird and signed it with their or encrypted with their secret key, then yeah, you could decrypt it with a public key, but we don't typically do that in normal use. A is also in the same vein. I mean, you can sign a document with a public key, but normally you would not do that. You'd sign it with your secret key. Which would you use to log accesses to sensitive files on a computer to make sure you knew which files were accessed and by whom? A public key, secret key pair. B, a hash of the computer's hard drive contents. C, a hash pointer to the config folder. Or D, a blockchain. I'm sure everyone here knows that it's D, a blockchain, but let's cover this right. Key pairs don't do logging, so a hash of a text file could be useful, but the text file may have been changed and rehashed right before it was presented to you, so you can't really rely on that. And a hash pointer suffers from the exact same problem. So when was it generated? Was it after the security breach? In this case, a blockchain is the only one that's useful here because you can't go back and tamper with the log after the fact, because you would then have to change all the succeeding blocks as well. All right, we know enough now. Let's design a cryptocurrency, right? We can do this. We got this down. And what I'm going to do is use some cryptocurrency concepts that came from the Princeton blockchain class, which I will link to at the end of this video. I lifted a lot of the material from that, and I thought it was brilliant, so I'm going to share it with you here. Here's Goofycoin, and here are our simple rules. It's signed by, so Goofy can create new coins, and here we have a transaction of him creating a coin with a unique coin ID, and he signed it with his secret key. And as a coin owner, he can spend it. So Goofy, in this case, owns the coin he just generated, and now he can pay it to Alice. And this is pay to the public key for Alice. And he signed it with his secret key, SK Goofy, and there's a hash pointer pointing back to the previous block, which proves that this is a valid block and he owned the coin that he sent to Alice. And the coin recipient, now Alice owns this coin, she can pass it on to someone else. So here she is paying this coin that she owns to Bob. She puts a transaction that says pay to public key Bob, and she signs it with her secret key signed by Alice and a hash pointer pointing back. So this is great, and we have a cryptocurrency. However, we have a big security problem. And what do you think that is? It may not be obvious at first, but what if Alice decides to pay Cinderella the same coin? So here's another valid transaction. Pay to public key Cinderella, hash pointer pointing back to a block that shows she owned the coin, and it's signed by her secret key. So everything here is valid. What then? This is a big problem, and this is what's called a double spending attack. And a double spending attack is actually the main design challenge when designing a digital currency. This is one that wasn't solved before Satoshi created Bitcoin. It wasn't solved in a decentralized system. Let me paraphrase. It was solved in Visa, MasterCard, bank systems, PayPal. I mean, they solved it, but they all needed a central server. So let's fix that same problem, and we'll create a new coin called Scroogecoin. And in this case, we'll have the same rules, except Scrooge will sign the entire history. And so here's a rudimentary blockchain. Here are 3 blocks, 71, 72, and 73. Each block has a hash pointer pointing to the previous block. And to prevent double spend, we have Scrooge that creates the authoritative hash pointer that points to the last block in the blockchain, so that we all know what's the valid one. So this is cool. It does fix the double spend because Scrooge won't let that happen. And verifiers can see the coin was already spent. But there's some other problems. And do you see the problem here? It's centralized. This is a problem because what if Scrooge decides to create too many coins, and you said, I only thought there was going to be 10 million Scrooge coins, and now there's 100 billion. He keeps making a new coin whenever he needs to pay a bill, and now my currency's devalued. Or what if Scrooge lies and says, hey, Alice didn't pay Bob that coin. Alice paid Scrooge that coin. And he makes a block that says Alice pays Scrooge, and then he hash pointers to that. Says that's the valid block. So if he lies, then what recourse do you have? Or what if Scrooge stops doing his job, and now there's no hash pointer that points to the most recent block that it's pointed to a block from 4 months ago. The currency is now ruined. So this won't work. We need to come up with a better system. Basically, we're asking, how can we de-Scroogify Scroogecoin? Let's talk about how Bitcoin achieves decentralization and the other cryptocurrencies that followed in Bitcoin's footsteps. What do we need to do to decentralize Bitcoin? Or in other words, if we unplugged all the servers at your bank and all your bank's branches, what's going to fail? And why would it fail? So here's some things to think about. Who maintains the ledger when you decentralize? Who has authority over which transactions are valid? Who creates new currency? Who determines how the rules of the system change? And how do Bitcoins acquire exchange value? This leads to the key challenge in decentralizing a cryptocurrency: distributed consensus. So what if 8 of Facebook's databases said you liked Nickelback and 4 said you didn't? What's the truth? Is 8 greater than 4? Does that mean that you do like Nickelback? Or maybe you updated it just a minute ago and it hasn't propagated to all the databases yet. So what is the truth? And this is the problem of distributed consensus. So remember, Bitcoin is a peer-to-peer system. When Alice pays Bob, she broadcasts the transaction to all Bitcoin nodes. So here's a transaction, pay her coin to Bob, and she signs it with her secret key. But if you notice, Bob's computer is not in the picture. This is a peer-to-peer system. Bob's computer doesn't need to be turned on. He can be sitting in the middle of a boat in the Pacific Ocean with no access to the internet and all of his computing devices shut off, but he still owns that coin. All right, let's learn how Bitcoin makes consensus possible. First off, Bitcoin introduces incentives, which is possible because Bitcoin is a currency. Bitcoin embraces randomness, and it does away with the notion of just one specific endpoint controlling the blockchain. Consensus happens over long time scales, about 1 hour. All right, do Bitcoin nodes have identities? True or false? Now, what I mean by Bitcoin node, I mean a Bitcoin server, a Bitcoin miner. It could be your wallet on your phone when you use to buy a cupcake. Is there an identity? The correct answer here is false. Now, I know we said earlier that public keys are identities, and in that sense, there are identities. But what I mean here, though, are identities like IP addresses or email addresses or perhaps your name. Those identities do not exist in Bitcoin. And why? Well, identity is hard in a peer-to-peer system. There are things like a fake identity, like a Sybil attack. So you can't rely on identity in the network. You can't say, this is the approved whitelist of servers that can process transactions in the Bitcoin network. We can't do that. So we have to achieve consensus without identities. So no one needs to have an IP address put out there as an approved list or anything like that. Anonymity is not a goal of Bitcoin. We're looking for pseudonymity. That is a hard word to say, by the way. So here's how the consensus algorithm in Bitcoin works. Simplified a bit, but this is the gist of it. New transactions are broadcast to all nodes. When it's broadcast, we call that zero confirmations, just FYI. Each node collects the new transactions into a block. In each round, a random node, a random miner, gets to broadcast its block to the rest of the network. And then other nodes accept the block only if all the transactions in it are valid. And by valid, I mean unspent, valid signatures. And then nodes express their acceptance of the block by including its hash in the next blocks they create. So they just build on it. They don't say, I agree that block 1000 is valid. They just say, here's block 1001, and it also includes block 1000. So block 1000 I agree with is being valid. So what can a malicious node do? Let's say Alice pays Bob and buys his car from him, and Bob wonders, when should I hand over the keys and be confident there will be no double spend? He could wait when the block first shows up with that transaction in it, and this would be a one confirmation here. But what if Alice also created a second block where she paid the same Bitcoin or cryptocurrency that she paid to Bob? She just pays it back to herself, to another identity that she owns. And this would be a problem because it's a double spending attack. So honest nodes are going to extend the longest valid branch. In this case, a Bitcoin miner doesn't know which one's valid and which one isn't. They both look valid from the perspective of a computer. And so if it builds upon the block that has the bad transaction in it, where Alice pays herself, this would be a problem for Bob because his block with the green transaction in it won't be included in the consensus branch, in the valid branch. And so he will have been out a car if he handed over the car too early. So this is what it would look like from Bob's point of view. When Bob sees this transaction hit the network, his phone will say, oh, your money's coming, and this would happen instantly. You would get this notification within seconds of when Alice hits send. So Bob at this point could decide to hand over his keys and start walking to the bus stop. But he may decide to wait a little bit for some confirmation. So when the first block gets onto the blockchain and the coin from Alice goes to Bob, that's called one confirmation. And this would take 10 minutes or less. Each block in Bitcoin takes around 10 minutes to be made. Then this alternate double spend attempt could also happen, and Bob might just be watching and making sure that everything's cool before he hands over the keys. So at this point, I would say, Bob, don't hand over the keys yet. Alice is malicious here. She's got a history. You just don't want to hand over the keys. So he could wait. But now let's say a next block comes over, and this would be the second confirmation, and it builds upon the good transaction block. And at this point, he might want to hand over his keys. It's not a bad idea, but he could wait. And then there'd be a third confirmation. And at this point, it goes on and on and on. And a lot of times people say wait for 6 confirmations before you sell the pizza or whatever. And I just think that's a little overblown. What you're waiting here is for decreasing the double spend probability so that it's basically 0. And after 6 confirmations, it basically is 0. But to paraphrase Andreas Antonopoulos, it's kind of overkill for 6 confirmations. He said he'd sell someone a cup of coffee, or probably more, for 0 confirmations. That's the dotted line there. That's 0 confirmations. For 1 confirmation, he'd sell someone a flat screen TV. For 2 confirmations, maybe a really fancy flat screen TV or a cheap car. For 3 confirmations, a really nice car. For 4 confirmations, a fighter jet. For 5 confirmations, an aircraft carrier, and for 6 confirmations, OPEC's budget for a year. Why? Because the amount of electricity that you would need to do to have that modified block would cost so much money that you basically need the budget of a small oil-rich country in order to even do that. It's just really. It's silly that anyone would do that after 6 confirmations. Double spends are really hard to do, and they cost a lot of money, and they're just not worth it because you can only do a double spend. That's the worst. You can't change, you can't lie and change someone's transaction because you don't own their secret key. So you can double spend. So what is the protection from double spending from? A, cryptography, B, consensus, or C, both? Correct answer here is consensus. The longest chain is because of the consensus of the blockchain. Now, cryptography is part of the blockchain, and we use it with hashes and signatures and whatnot. But cryptography can't distinguish between a true transaction or a malicious one. The consensus will protect the vendor from a double spend, even if the nodes are malicious, because you just wait for the longest chain to be extended, and once you feel comfortable with the correct number of confirmations, you can then part with the item you're selling. So recap here. Protection against invalid transactions is cryptographic. Yes, crypto is involved, but it's enforced by consensus. And protection against double spending is by consensus. So at the first broadcast of a transaction, you're not 100% sure it's in the consensus branch yet. But after about 6 transactions, the odds of a double spend are pretty much 0. So, depending on how big the item is that you're selling, you probably can sell it after fewer confirmations. All right, we now successfully have created a cryptocurrency that can work, thanks to Satoshi Nakamoto's design of Bitcoin. So we use our hash pointers to give us confidence that the data hasn't been modified. We don't have a centralized party responsible for handing out identities or for pointing to the most recent block. That's all done with random proof of work. And then a consensus can give you confidence that your currency hasn't been double spent. And so, good job, everybody. We have designed a cryptocurrency that can work because the blockchain is now magic. As I mentioned, I'm Paul Oliver, and that's my Twitter handle there at @It'sPaultastic. Thanks for watching my video. If you want to subscribe, click to the left. If you want to watch the Princeton Bitcoin course, click on that channel to the right. And I have a couple more videos at the bottom that might be useful or interesting to you. Thanks again for watching, and please come back for more.